Hi, I'm Dr. Courtney with the Quantitative Reasoning Center. So we want to talk about today three of the aspects that are very important in a challenging course like multivariable calculus. One is the qualitative understanding of the problems and the techniques and what's really happening. How do we interpret the numbers and the results of a mechanical computations in terms of the meaning of multivariable calculus and the physical systems that multivariable calculus can be used to treat. The second important aspect of the course is the mechanical computations. How do you compute partial derivatives? How do you compute directional derivatives? What are the mechanics involved computing divergence and gradient and curl of given functions, and how do we compute multivariable integrals? And the third aspect of the course is technology. How do we bring technology to bear to better visualize, to better help us with mechanical computations and to better interpret what's happening? And several mistakes are often made in the course where students feel like their comfort level and their skills in one or two of these areas is going to carry them through and help them both succeed in the course, as well as giving them all the prerequisite skills that they should gain in this course to succeed in the downstream courses like engineering mathematics, like the higher level engineering and physics courses, and like differential equations. So we don't want to have strong mechanical skills and neglect technology. Nor do we want to rely so heavily on technology that our mechanical skills are weak or that we're unable to interpret the meaning of the bottom line that the technology provides us. We really want to make sure as we finish strong in the course that we're competent in all three areas. Okay, so we're having a look at 16.1 number 19, and the task is to plot the vector field that we're given and find a set of points so that the vector field is equal to 0, and to use that to help interpret and understand the plot of the vector field. So the big idea is to plot, and we're going to use the vector field analyzer and interpret the vector field. So to develop the problem, we're going to use the vector field analyzer to draw our picture, and that's a big part of what's going on here. So I strongly recommend that as you're working problems in chapter 16, anytime it makes sense, even if it's not a specific requirement of the problem, you should plot the vector field in the vector field analyzer. Because what this helps you do is it'll help you develop an intuition for what's going on with different vector fields that look like different things. And as your intuition grows from seeing lots of examples plotted, then your skill will grow along with it. And then for the second step of our plan, so use the vector field analyzer to plot it, we're going to set each component, because if a vector function is equal to 0, what that really means is that each component of the vector function is equal to 0. Alright, so let's go ahead, and while we're still at the whiteboard, let's do that, and we can see if we can use that to anticipate what we're going to see. So the x component basically says y squared minus 2xy. This is the x component of the vector field. And if we set this equal to 0, well, we can factor this a little bit, right? We can factor this out of y. And so this is y times y minus 2x equal to 0. So this has two solutions, y equals 0 and y equals 2x. So this is the x-axis, and this is the line y equals 2x. So what this tells us is that along the x-axis and along the line y equals 2x, the x component of our vector field is going to be 0. Alright, now let's think about the y component. We have 3xy minus 6x squared equal to 0. So let's kind of give our outline here. Now this is the x component, and this is the y component. So now we can factor out a 3x, and we get y minus 2x equal to 0. So this is the y-axis, and the y equals 2x is the line y equals 2x. So what we found is that the x components equal to 0 on the x-axis, the y components equal to 0 on the y-axis. But both components are equal to 0 along the line y equals 2x. So if we think about that, the line y equals 2x in the xy plane looks something like this. So what we're expecting is that anywhere along that line y equals 2x, our vector field, both x and y components of the vector field, are going to be 0. So we expect the arrows in the vector field analyzer plot to be very, very small, close to the line y equals 2x. Alright, so without further ado, let's go ahead and move over to the vector field analyzer and get a little practice with that marvelous technological tool. Straight to the Arizona State University website where I could fire it up. So this is just the default vector field that is already plotted in the vector field analyzer, and so it's not the function we want. We want the x component of our vector field to be y squared minus 2xy, and we want the y component of our vector field to be 3xy minus 6x squared. And then all we do is we click on plot this field, and it plots the vector field. And there are some other options that are very nice. You can center the window at any xy coordinate that you want. You can set a size of the window, so you're basically setting what the range is for your situation. And there are different, you can zoom lenses, you can look at differential equations and flows, and then there's also this other tab here to look at line integrals. And these options can be very useful a little later on in the chapter. But for now, we've just plotted the vector field because this question didn't ask us to do a whole lot. And what we were expecting is we were expecting the vector field to be 0 along the line y equals 2x. So if we go ahead and we draw in the line y equals 2x, that's something like this. Actually, that's not the best drawing in the world. So we go ahead and we draw in the line y equals 2x, and we can see that as expected the vector field arrows get very, very small close to this line, as we would expect, because our whiteboard computations a few minutes ago showed that near that line, or at that line y equals 2x, the vector field indeed goes to 0.